So in the last class, we we touched upon the operation of low pressure CO2 laser, where the gas pressures can be of the order of 10 to 15 to 20 millibar, and a longitudinal discharge is what is affected. And normally one sees the glow discharge because the mean free path, which is inversely proportional to the pressure, is quite large, and therefore there are the possibility of instabilities or constrictions are very less, and one normally sees a glow discharge. These, whatever I said, they are called diffusion cooled type of CO2 lasers, because the heat that is dissipated into the gas. Why the heat comes? We know that heat comes because you have your 0, 0, 1, 1, 0, 0, 0, 2, 0, 0, 1, 0. So while you have lasing here, these are all VV transitions, so there is not much energy loss or gain involved. But from here to here, this transition, it goes into VT relaxation. That means it goes as kinetic energy of the other gases. Kinetic energy means it increases the thermal energy, and this heat, this excess heat of this is conducted away by means of addition of helium, which goes and hits the walls, diffuses to the walls. Why we use helium? Because helium is light, it can diffuse faster, it has a high thermal conductivity, and therefore it takes away this heat, gives it to the walls, and from the walls it is conducted away by means of cooling jacket. This is one way. Then, so, and what happens to the gas? Well, what normally is done is that the gas flows in, it also gets heated up. That heat is conducted away, we are saying, by means of cooling jacket. But in the discharge, what happens is that the CO2 gas, when it collides with energetic electrons, it can get dissociated into CO and oxygen. This is a reversible reaction, but initially your concentration of CO2 is so high that this forward reaction is much more active, and therefore formation of CO and oxygen takes place inside the discharge. So that means what? We are saying that the gas gets contaminated. This gas gets, we wanted CO2, helium and nitrogen, but there is a formation of CO and oxygen as well. And what is the problem with CO and oxygen? The problem with CO and oxygen is that CO can depopulate the upper laser level. That means when we say we have 0, 0, 1, we have nitrogen B equal to 1, which is effectively transferring population kinetic energy, which is storing energy and is transferring the population. Now, nitrogen is allowing us for selective excitation, but this CO has the effect of depopulating the lower laser level and thereby killing the population inversion. So that is a problem with the formation of CO. And oxygen, we know, has a high electron attachment capacity. That means oxygen can easily form negative ion, and therefore it takes away the electrons which are created in the discharge. That means electrons are consumed up in the formation of negative oxygen ions, and this, you require a sufficient number of electrons for initiating the discharge, for sustaining the glow discharge, and therefore we do not want any species in the discharge medium that will remove the electrons and create a problem for the sustenance of the glow discharge. Therefore, this CO as well as oxygen, which are created in a discharge, they are detrimental for a glow discharge, and therefore normally what is done is that although the heat is conducted away by using a water, by flowing water, this gas is also replenished from the glow discharge zone by means of flowing it. So as you see here, the gas goes in and the gas comes out. The flow rate is decided from what we see, from the optimized output. We see when the discharge products are not too high to give rise to a good output. So until then you allow it to flow and then you get it out. So that fresh gas comes into the discharge zone, and therefore your output is not compromised. But then we know that what are our discharge gases? Lasing gas mixture, CO2, nitrogen, and helium. CO2 and nitrogen are okay, but helium, which is in larger proportion, it is very expensive and it is also very scarce. Right? It is a very light atom, and therefore it moves out of the atmosphere very easily, and therefore getting helium is very difficult. And therefore, when you want to increase the output of the laser, when you want to flow the gas at a faster rate, then throwing away helium is not a very nice option. And therefore, diffusion cooled but sealed off systems have come into existence. So what happens in sealed off system? As the name suggests, that it is a sealed off system. That means we do not have this gas flow in, flow out system. So then how we take care of this dissociation problem? Well, what happens is that this discharge tube is lined, or it is sputtered, or it is coated by certain catalysts. These catalysts, they hasten the reverse reaction. That is, CO plus oxygen plus this catalyst gives rise to the formation of CO2. So that means the dissociation products, which are CO and oxygen, are recombined in presence of this catalyst, and therefore the catalyst is lined, it is coated on the outside walls of the discharge tube, as you can see here. And the thickness of the coating, the temperature that is required for the coating, etc., are so decided that it functions well in a discharge region. So the catalysts generally used are gold catalyst, silver oxide, palladium, etc., which can operate at that discharge temperature conditions. And sealed off systems nowadays are quite well developed, and you can have almost 2000 hours of continuous operation for even outputs as high as 200 watt. So the use of sealed off systems is that it makes the system more compact, more user friendly. In addition, the wastage of helium that we have seen in a flowing gas system can be overcome. Yes. Now, we always want higher and higher output power from a laser system. Why? Because there are many applications which require higher power. Something which you can do at lower power, but there are certain applications which require higher power, and therefore we would want to increase the power. So how can you increase the output power, CW power, from a laser? The first and most easiest thing that comes to our mind is increase the pumping power. You increase the discharge current. So if you increase the discharge current, you create more electrons. You create more population inversion, because you are exciting both nitrogen and CO2. So you create more population inversion. If you create more population inversion, you have more stimulated emission rate. So higher the stimulated emission rate, more will be the intracavity flux. And more is the intracavity flux, more will be your output power, isn't it? So that is the easiest way. But then what happens? As you increase the pumping power, yes, we will have an increased stimulated emission and you have a higher output. True. But as we know, higher output means there is also higher heat dissipation inside the system. And to take care of this heat dissipation, you will have to remove also this heat that is generated. So you can only increase the water flow rate to some extent, but that is not the solution. So what normally is made use of is you remove the gas, make it go through a catalyst. So what is the catalyst doing? Catalyst is actually trying to see that the dissociation products are recombined into CO2. The CO plus oxygen plus this catalyst will give rise to CO2. So the contamination part of the gas is taken care of. Then it goes to the heat exchanger. So what the heat exchanger does, it takes away the heat and the cold gas is once again made to flow through the discharge loop. So here we are forcibly drawing the gas, making it go through a chamber which has a large catalyst, because here just lining probably will not be efficient, because in case of lining the gas has to diffuse to the wall, get recombined and then again be available. But when you want to increase the power and you want to dump in more energy and get more output, in that case you want to draw, you're forced to actually remove the gas, make it go through catalyst, see that the gas is decontaminated, the CO2 is reformed, and then it goes through the heat exchanger where the temperature is removed, the gas is cooled, and it is once again made to flow. So this is called a fast axial flow system. The gas flow is quite fast and it is also recirculated, and in this way several kilowatts of CW output power is possible. But again, if you want to further increase, then what do you do? So to increase further, what are we doing here? We are flowing the gas axially, means all along the length of the discharge tube. As I said, increasing the length, like suppose a typical length is about 1 meter. So you are flowing the gas all along the length, and therefore the pressure head, that means requirement from the pump, the roots blower, becomes high, and therefore you have to use high capacity roots blower. So if you want to increase any further, then the limitation comes from the pumps that we are going to use. So the other method is to make use of transverse gas flow. That means although you have the discharge longitudinally, we are not flowing the gas longitudinally, but this is the cross-sectional view. We are trying to flow the gas transversely so that the pressure head is reduced and you can make use of a centrifugal blower. And once again, the hot gas is removed. It goes through the catalyst, goes through the blower. You have the heat exchanger, which removes the heat, and then it is once again fed into the discharge zone. Only difference between this and this is that here you have an axial flow, that means all along the length axially, whereas here we are flowing transversely. You can imagine the gas flow in this manner, right? So the construction of these are a little tricky, and but with this, because you can flow the gas much faster, the pressure head is less, so the requirement on the pumps is also reduced. Therefore, you can go to a faster rate at which the gas can be replenished, and therefore here tens of kilowatts of CW power has been obtained. One basic difference, as I have said, is the way in which the gas is removed. In this case, it is axial. In this case, it is a transverse. But the quality of laser output, the spatial quality of the laser output is supposed to be better here as compared to the transverse gas flow. But these are certain ways of getting higher output. Now, one more method that you would think, why did not we discuss it before, is just by increasing the gain length. See, we said 1 meter will give about 50 watts. So if I take 2 meters, I should get 100 watt. And if I take 3 meters, so on and so forth. So just by increasing the length also, we are increasing the active medium, right? The increasing the active medium, you should be increasing the output power. So yes, this method also has been tried. People have tried to go for longer cavity lengths. However, one problem with this longer cavity length, as you can see, is, see, we are striking a discharge between the two ends of the cavity, right? So longer the length, the requirement on the high voltage power supply becomes much higher. So you need to have, if it were 1 meter, you may have about 25 kV DC power supply. But the moment you go to 2 meters, then it has to become almost 40-50 kV DC power supply. So that becomes a limiting factor. Another limiting factor is alignment of the mirrors. You see, the two mirrors have to be aligned, and this tube, which normally is a perspex or a quartz tube, so the straightness of the tube becomes very, very important, and therefore this gives rise to alignment issues. So this kind of increasing the CW power by increasing the gain length simply in this manner is restricted to not more than 2 to 3 meters of cavity. The other method is, okay, you do not have a single long discharge, you have many discharges. For example, I have shown here many discharges, 1, 2, 3, 4 discharges, right? Each has its own power supply, right? This has its own power supply, this has its own power supply. Only they are optically in series. That means the photons which are starting from here, suppose they go, get reflected from here, go through the other discharge, go through the other discharge. So they're amplified. Amplification is happening in every tube. So these are optically in series. You can think that this is one mirror and this is the other mirror. Okay, this is one mirror and this is the other mirror. Only difference is that we have not kept them in linearly, and we have not used a single power supply. So this is another way. People have tried this also in zigzag geometry, V-shaped geometry, etc. And maybe about 1 kilowatt output with some 7 or 8 segments have been obtained. This is one way, but then the problem with this, or difficulty with this, is that we are using so many high voltage power supplies. You see the number of discharges, you have those many independent power supplies. Then there can be voltage flashovers. We are talking about say 1 meter, I'm saying 20-25 kV DC. So when you have 25 kV DC, then there can be voltage flashovers which become very common, and therefore this is one method where people use for limited output. For example, 500 watt or 250 watt, 300 watt, such kind of zigzag configurations are used, but not beyond that. So far, we have only seen of how to increase the laser output power in CW condition, and we have seen that we can increase it by increasing the gain medium. We are increasing the length of the cavity. We are trying to force. We are replenishing the cavity, the gas mixture very fast, so that newer and newer gas mixture comes into the system, and you can pump it harder, try to get more output. So these were the ways. So fast axial flow, transverse flow, or large cavity lengths, segmented discharges, V-shaped cavities, etc. were part of that. But we did not. Suppose we want to go from kilowatt to megawatt. So then how do we? That is a big change, and it is not really possible simply by increasing the gain medium, increasing the cavity length. So here we want to increase the number of lasing molecules per unit volume. That can be done by increasing the pressure. So now we come to operation of CO2 lasers in the pulsed format. At high pressure. So in high pressure, automatically, as I said, I think of pulsed. Why? Because at high pressures, CW operation becomes very difficult. Why it becomes difficult, we will just see. See, this was our CW system where uh, we had anode at one end and we had cathode at one end, and we said that the stray electrons which are in the gaseous medium, they get energized, they create further more electrons, and these electrons create even more electrons. An avalanche of electrons is created, and this gives rise to a glow discharge between the two electrodes. Now, a glow discharge, what do we mean by glow discharge? When we say glow discharge, we mean that the number density of electrons in any given volume, number density of electrons in any volume is nearly same. So the number of electrons in any given volume, when it is equal, then you have a uniform flow of current. The current from anode to cathode flows uniformly through the entire active region. It gives rise to uniform excitation of the molecular species which we are trying to excite, and you have a good excitation basically of the species, and you have a good spatial profile also of the lasing. But as the pressure increases, now we have seen that you have stray electrons everywhere. Now the number of these stray charges in any given volume may not be equal. There can be more number of electrons here. You have so many more electrons, whereas here you have, in this volume you have few, in this volume you have even few. So the number of electrons, the stray electrons, need not be equal in the discharge volume. So these are called instabilities. Now these electrons in low pressure, in the low pressure, your mean free path, where lambda is called mean free path. What is mean free path? Mean free path is the distance traveled by the species between two collisions. So this mean free path is proportional or inversely proportional to the pressure. Higher is the pressure, smaller is the mean free path. That means it collides very, very more frequently. Smaller is the pressure, it travels faster before it sees another species for collision. So as the pressure increases, the collisions become so many more that the electrons, suppose we consider the electrons here, these are already larger in number. They collide more, they gain energy, collide more, create more electrons in this region. They create more electrons in this region. So these electrons, before they can diffuse out into the other volume, they create more and more ionization in very localized region, and therefore the current then that flows will be highly localized. This is called an arc discharge. Why it is localized? Because the instabilities that have been that are already present in a which are already present anywhere, these instabilities do not have a chance to diffuse out. They don't have a chance to diffuse out because the mean free path is very small. That means there are so many more collisions that they cannot diffuse out into the entire volume of the discharge. And because they are not diffusing out, they are creating more number of active species, the electrons, in a very localized region. And because there is a very localized region, the current flows only in this localized region. That means the entire active volume is not energized. You have an arc discharge, so you have very, very inefficient excitation of the active species, So what is the active volume now? It is just the region where you have the arc. As you can see here, this is the arc region. You can see that this is the arc region. So this is the volume. And in this volume, you have electrons. So efficiency of excitation is extremely low. So this will be a highly lossy system. And therefore, the gain can never be met with. And therefore, you cannot have lasing. So at high pressures, to avoid this arc discharge, this glow to arc transition. What is meant by glow to arc transition? When you apply voltage, it initially begins with glow because there are not too many instabilities. There are instabilities, but they have not yet become too localized. But once a current starts flowing, then you can see that these instabilities tend to grow. And as they tend to grow, this glow discharge degenerates into an arc. And what you have is an arc discharge. So this glow to arc transition time, it reduces with increasing pressure. At low pressures, like 10 millibar or so, we know that it remains in glow discharge because these instabilities do not have any time to diffuse out. They always diffuse out. I'm sorry. At low pressures, their mean free path is so large that they do not aggregate, they do not coalesce, they do not result in this kind of arc formation. But as the pressure increases, the glow to arc transition time reduces and the glow discharge tends to become an arc. So at atmospheric pressure, it is few tens of nanoseconds that your glow degenerates into an arc. So the remedy, what it is that don't have a CW discharge. You pulse your discharge and let the discharge duration be within the time glow to arc transition takes place. So if it is within that glow to arc transition time, then you ensure that you have a glow discharge. And in that time, you can have population inversion. And also because your lasing species population is very large, you're operating at atmospheric pressure or even high pressure, so you can aim and you can get much higher peak powers. So we come to therefore a pulsed operation of a CW laser where megawatts of peak power is possible. I will just very briefly tell you this maybe if you have had some electronics background or electrical background, you will be very easily able to grasp it. But I will tell you very briefly in a very simple manner. So basically, it is the same thing. This is your laser load. Okay, this is what we are saying is our laser, the two electrodes of the laser. Okay, and we have a high voltage source and we charge a capacitor through the charging bypass. So when the capacitor is charged to the required voltage, then this switch closes and the condenser discharges through the switch into the laser. So you can see that the condenser is made to discharge into the laser. Now the discharge duration of the condenser into the laser loop has to be kept less than the glow to arc transition time. So if the discharge is within that time, then you can have a glow discharge in between the electrodes where you have filled in your laser gas mixture, that is CO2, nitrogen, and helium. And once you have so when the condenser discharges, you have a current pulse, right? So this current pulse, while in CW it was a continuous, now you have a pulsed current pulse, and this current pulse will now excite the active species inside, will excite nitrogen, will excite CO2, nitrogen will transfer its vibrational excitation to the CO2 molecules, you will get inversion. And advantage here is that you have taken the laser at high pressure, maybe an atmospheric pressure or even higher. And therefore, your population, active species density is much higher. So we will continue with it later in the next class. So we end here, and we have seen the CW operation. We have seen why CW discharge is not possible at high pressures, the circuit that basically governs the pulsed operation of a CO2.